Okay, so welcome back. I added to the README file, all kind of links that I showed you. One thing that I still wanted to mention that I also added is that there is going to be a Python conference in Israel in September. It's the PyCon is the name of the conferences, the Python conferences around the world. There are various places with this name. So in Israel, there's going to be in September. They're going to announce the presentations soonish. I don't know when. We'll see. Okay. So that I would recommend that, and I think I added a link to it to PyCon Israel here in the links. So that's it. Pandas. A little bit about pandas. Pandas. The idea of pandas is to deal with what they call data sets. And the data set is basically just a representation of an Excel file or a CSV file for that matter. One page in that. Okay, so not the whole file. I mean, yeah, okay. We can call it a representation of that. The idea is basically that you have some table-like data, and you can store it in Excel or CSV or all kind of other places. So, for example, here we have a CSV file that looks like this. We have a planet and the distance and the mass, and then we can do this. There's some other data we can download. Like this is an old link, but from Stack Overflow, the one I mentioned, they do a survey every year, and they distribute the raw data after removing the personally the things that you can identify personally. People they remove it, and then they distribute the data so people can do their own analysis on it, and so on. There are lots of other places you can get data from, but I guess most of you will have your own data, so you can use that. With the Planets CSV, this is the way we use it. We import pandas, and again we just with NumPy here too. We are using a shortened name. Usually it's PD, and then you can call pd.readCSV. You give the name of a CSV file, comma-separated values, and it will get you something which we call data frame, and therefore the common variable name that people use is df. And I can print out the df itself, and it will show you the same data in a nice-ish format. It also numbers the rows, the titles, column titles are there, and so on. But basically, each one of these columns is a NumPy array. Okay, not together, because together they are different types, but in each individual column is a NumPy array of its own type. So you can then ask various generic things about these data frame, what of the list of columns, what of the types, the data types, and this goes back to NumPy. So it shows you the titles, which each one what type it has. It's float 64, folks. That's from NumPy. Object means basically text, so that it doesn't know what specific number to use. You can get the values, and you can use describe, and describe basically takes those columns from the CSV, from the data that are numerical, and those are stored in NumPy, and NumPy provides those statistical methods that you might recall that we saw, and it does the same. It just calls those and displays all that generic statistical data that can be useful to get some feeling of the data. The count is interesting, that it also shows how many values you have in that column, and it's important because sometimes data is missing. So in this case, every column has 11 values. Pandas has, I'm not sure if it's in the slides, but Pandas has ways to define what to do if a piece of data is missing. So you're loading in the data from a CSV file in the same way, I get back to here, the same as you have read CSV, you can also have read underscore Excel, and it will read from an Excel file. And then you can provide all kind of other ways, other parameters for the loading. For example, telling it how to handle missing data. Okay, whether it should put 0 there, it should mark it as missing, it should put the average of all the other numbers in there. It all depends on your data, how you would like to handle that. Yeah, so this is the same thing with, I guess, some different data. Okay, some slides are not that useful here. Okay, here you can. Okay, so for example, here we have some file where you have, I don't know where the file is, but the file has a column with numbers with an exit code. And the exit code can be either 0, meaning success, or some other number, meaning failure. And what I wanted to here is to have a true or false as the exit code. Okay, so this way I could provide converters for my data. So when I'm reading in the data, it can do all kind of conversions as I'm reading in the data. We can split up multiple values from the column. You can all, in a nutshell, you can do all kind of really, really fancy things with the data. I think here, what we had here is a data that looks like this. I had 2 columns. The first is some name, and the second one is either a single fruit or a list of fruits separated with comma by itself. Okay, why is the data look like this? I don't know. Someone provided it this way. Okay, some machine, some other program generated the results of some experiment in this less than ideal format. Fine. How can we deal with this? Let's say this one. What we did here is we got back instead of this, that would be the default way of reading, and here NaN means not a number. It basically means the value was missing. So let's see, Bob, right? Bob doesn't have any fruits. Okay. Instead of that, I converted into this not matrix, data frame. Okay, where we have the name, fine. The original fruits, fine. It's the same thing. But we added for each type of fruit, we added a Boolean value, whether that was in this row. Okay. And maybe you need something else, of course. But this line allowed me saying that if basically I created a lambda function. Okay. So on the fly, I don't need to define a name for this function, because creating a named function means I have to come up with a good name. Okay, I can't just call it I don't know, conversion. I need a good name. But if I use lambda, I don't have to come up with a name. That's really good. Okay, so lambda function gets one parameter, which is the current row, and it says, okay, in the row there is the fruits field, and we check whether it's not null. Okay, so null would be represented here as NaN, not a number, but not null basically means it has some value there. So if it's not null and the value is in the row of fruits, okay, so this is basically what we are doing here in a loop, then we are creating true or false. Okay, so this is actually not during reading. Maybe I could do it also during reading, I'm not sure. This happens after I read, I change the data frame and add more columns. So I enrich my data. That's the missing proper word for it. I think this is just a different way to do this. You see? Yeah. This pandas allows me to see the first few rows with head, the last few rows with tail. It's useful. I mean, you will have a data set with thousands or tens of thousands of rows of data. You don't want to just print everything on the screen, but you would like to take a look at the data. So you can ask it to show you the first few lines, last few lines, specific row, this column, that column. You can make it easy. Now, the thing is that right now I'm showing you slides and showing you programs with .py extension that I would write in Visual Studio Code. Many people use some interactive environment, probably Jupyter Notebook, and then while they are writing this code, they can already see all these things. So they can interactively interrogate basically the data they get from the CSV Excel files and so on. Yeah, we are just selecting columns here, not that interesting. Yeah, okay. So here we are taking two columns of the data frame and multiplying them. These are basically, remember, each of these columns are a NumPy array. So you can do that behind the scenes, okay? So you can do operations like this and then assign it to a new column in the data frame. So now you have here this DM, which is, what is this? Distance times mass. Okay, and then we do some, okay, so this is a series of examples with some calculations with the data in that CSV file with the planets, calculating the force on each other and so on. Some physics things. It's a good thing that I have this physics example because most of the students are biology students here, so they might not understand much more than I do. Okay. Yeah, I had one of the students who was actually, this was their area of research. So it was interesting, trying to show off as if I knew something about this. Yeah, so here we are just again just different ways of reading the data. Okay, so this one is already showing you a histogram. Okay, so here what we did is I took some CSV file called survey results, read it from the file, and it has so this is the Stack Overflow survey where we have one column basically asking which country are you from. And so I wanted to see where are people from. And this is the value counts, okay? And then here we displayed the top 20, I think. And then I created a histogram with the bin size of 20. Okay, so because I mean, there are 100 something countries, I wouldn't be able to show it nicely. So the bin size is 20. So now you can see that what you usually think that very few, most people are from a small set of countries. Most people are answering. So they're usually US and UK and a couple of these countries. And then all the rest of the countries have very few responses. But of course, your data will have its own interesting stuff.
Okay, let me try to show you. No, I'm not sure if I can show you. So a little bit explanation. What I wanted to show earlier, and then I didn't find the actual data for it, is machine learning was from here. And yeah, we can try to do it. Jupyter Notebook. I can try to go over this one. Yeah, so there is a rather famous data set called the Iris CSV, the Iris data set. It comes sometimes in this and sometimes in that format. Is basically a set of data someone measured 100 years ago. It's like 100 years old at least. Took irises and then measure the petal lengths and widths and the sepal lengths and widths of each of these flowers. And then basically there are three types of them. The setosa, I have no idea what they are. This one and the third one, okay? And the idea was, the question is, given these data, so, okay, I can easily measure these ones, okay, right? You go to the flower, I can easily measure that. Can we, from this, tell whether which one of the species are we seeing? Okay, that's the big question. And this is a question for basically machine learning these days. 100 years ago, it wasn't that much of machine learning. Okay, so we have this. I think this in this file we have 100, 150 or 200. How many? 150 values. So I have here somewhere a notebook for this. Okay, that I think I prepared or yeah. So there's a website called Kaggle where you have tons of these data sets. So if you don't have your own data set and you would like to practice, Kaggle is a very nice place where you can get all kinds of data sets. You can upload your results. You can read other people's solutions. Fantastic for someone who would like to learn this stuff. Okay, so let me try to import all this. Okay, it's complaining. Seaborn is not found. Okay, let me stop this whole thing. No. Sorry. Let me show which Python. Yeah, this is using the right Python. So I have to just install pip install Seaborn. Apparently it's not installed for now. So I'm installing it. So you can see, I think I showed you that from Jupyter Notebook, you can run commands that are not part of Python. So this is something that I would run on the command line, but I don't want to get out from the Jupyter Notebook, so I can do it here. Now let's try to execute this. Now whatever sklearn is still missing. Okay, so sklearn. I also add it. Actually, I should add everything here. Pandas and NumPy and matplotlib, and then I will move to the top of this whole thing. So I can take this line. I don't need this one. Above this, I can add this and run. So it will install now everything that needs to be installed. And I won't be able to show you because there is some problem and it can't install something. Okay, that's very unfortunate, especially that I won't have time to fix this issue. Oh, scikit-learn. Okay, sorry, my mistake. It's not that sklearn. I need to install this package. Luckily, it told me. Copy.
scikit-learn. Yeah, this name exists for, I don't know, many years, so I don't know why I made this mistake, but happens. Okay, so now I hopefully installed everything, so I can run these things. Now, this is just importing all kind of libraries that we'll be using. One thing is here that I'm doing is saying np random seed and just giving it a number. Why is it that? This whole process of machine learning is based on some random numbers. Okay, it will generate some random number, and then based on that does all kind of things. So it has the data, of course, but it also uses random numbers. Now, if you start the random number generator in Python, as in every other programming language, by the way, by default is what we call a pseudo-random generator. So it's not real random numbers. It's just some numerical, mathematical series of numbers that behave as if it was, as it had, what is it called? Not normal distribution. As if it was random, okay? I forgot the name of the distribution, but as if it was really random. It looks like as a number. So if you look at the numbers as a statisticians, you won't be able to tell that it's not really random because it acts as if it was random. In reality, given a number from this, given one random number, you can compute actually what will be the next random number because everything is deterministic in a function. So from the point of view of a machine learning algorithm or just something like this is totally fine. If you would like to deal with secrets or encryption or stuff, then you need the real randomization. But okay, so now we have this pseudo-random, fine. And we run the machine learning thing and we get some result, okay? And then we make some changes and run the algorithm again, and we get some different result. But we don't know now if the change in the result is due to what we changed or due to the fact that the random generator generated different random numbers. In other words, you run the algorithm, you get a result. If you rerun the same algorithm again, you will get different result because it includes not only your data, but also some random data, some random numbers. Now, theoretically, okay, or if your algorithm works properly, then the difference between these results shouldn't be important for your paper, let's say, okay, or for whatever you are trying to prove. But if you're trying to now see that your changes, when you're going to make improvements to your algorithm, whether they had a positive impact or a negative impact, okay, then these small differences have meaning, okay? So in order to avoid all the problems that randomization creates for us, especially during the development of this thing, we fix the random numbers, okay? They still will seem to be random, but now every time we run the program, we will get exactly the same random numbers. So meaning that if you run the program twice without any changes, you will get back the exact same result. And if you make some changes in your code and you get back different results, you will know that your changes were the only things that impacted the result, okay, and nothing else. And as a researcher, you know that it's important to fix all the other moving elements. So this is what this np-random.seed does, fixes the random number. Why 123? It's a totally arbitrary number. You could put there anything, okay, any number, but you keep it fixed. and then this is going to be the random. These are going to be the random numbers. If you have any questions here, just ask. Second thing, we are loading in the iris.csv file, the one we saw earlier with the 5 columns. And when we can look at it and describe what it is, and actually not that. I call it described here. Yeah. So this one, we can see the statistical data on each one of them. Fine. I don't have much to do. I just showed you. Okay. Head will show you the first few columns. By default, the first 5 columns. Okay. Now what? Okay. And let me explain. Basically, what machine learning is trying to find a function that based on these 4 given 4 input values, it needs to give me, in this case, one of the 3 values. Okay, if you remember, we have in each column, okay, we have in each row, we have 4 numbers. This is just the ID, don't worry about it. 4 numbers and the species. And what we would like to do is create a function that, given these 4 values, will give up the species. Okay, this is called a categorization problem. Basically there are 2 types of problems. One of them is categorization. So given some input value, you need to pick one distinct value. Okay, the other one is the regression, where you have, let's say, dots and you need to put some, you need to create a mathematical function that, given every input numbers, it will give you a resulting number. Okay, so let's think about a linear function or a square function or something like this. Okay, basically that's what all of these machine learning things are trying to do. And there are various of these algorithms, various of these functions. Well, okay, let's have a really simple example before we get here. You have some data with an x and y numbers. Okay, just an x axis and y axis. You can dot them on an x and y axis. Okay, and now what you're trying to do is predict that, given an x, what will be the y. So you want to create a function, and you can try to put a linear function, a linear function on it, and it will be somewhat close to the reality. Okay, and you try to make it as close as possible. And you can have a more complex one. This linear function is not good really, because all the dots are really, really far away from this one. I mean, if you have only 2 points, you can have a line. But if you have 3 points, then suddenly you can't usually put a line through all 3. But if you have 3 points, you can have an x square function, right? That goes through all 3. And so if you have many points, you can have a very high order function that will be closer to the reality of those numbers. And basically, this is the whole story of machine learning, finding these functions. Okay, now what we do is, what we actually have is, okay, you get some data. In this case, we have 150 rows. What can we do now? We can use the 150 rows to train what we call some algorithm to let this system find the best function it can. And it will create a function. But how can we verify that this function works well? Well, in order to verify it, we need new data that we can compare the results. So but we don't have more data. So what we do is we take whatever we have, the 150 in this case, and we divide it into 2 sets. Better people, or not better people. If we were more advanced, we would divide it into 3, but for now, 2 is good enough. The first set of data, we are using to train our algorithm. Basically, we give it to the system and tell it, okay, please find something that will be a good match, that given these rows, given the 4 input value, it will give you the good result, the right result for species. Now, and we used part of the data for this. And now we have got an algorithm, a function, and we use the rest of the data to verify how good the predictions are. So in the rest of the data, we will put the input data, we will get the calculated, the predicted output, and we compare it to the measured output that we have it here in the system. And then we will see, did all of them match? None of them matched? 70% matched, okay? And how the closer you are matching 100%, the happier you are, right? And so this is the idea. So let's go back to the code. And this is what basically we are doing here. We're taking, so what we have here is the x. It's not, there are no x and y axes, right? There's not a single x and a single y axis. Basically, we have 4 things that together is the x-axis. So the custom is to put them in a variable called capital X. So I took the data frame and put all the data, all the x's here. And y is what we need to predict, which is the column from the species. Okay, so now we have all the x's here and all the y's in this variable. And now we need to split it. So for that, we have this function called train test split, which comes from the scikit-learn library somewhere. Train test split, yeah? And this sklearn library. Okay, so what it does, it takes all the x data and all the y data and basically splits them into 2 groups. One of them will be used, I think, and the default is to 2/3 for training and 1/3 for testing. But you can tell how to divide it, okay? So, and it will create us 4 variables, x for training and y for training, so the input for training and the result for training, and the x later for testing, for verifying the data, and the y for verifying not the data, to verifying the algorithm, and y to verify the results of the algorithm. There is one critical issue with this data though, okay? So in this data, I think we have 1/3 of each species, okay? There are 3 species and we have 1/3 of each species. Now imagine that the way they split the training data and the testing data, it will say, well, the first 2/3 is the training data and the last 1/3 is the testing data, okay? Now what happens is that in the training data, you only have 2 species, and in the testing data, you only have the 3rd species. So basically, the training data is totally useless to predict the other set of data because I have no connection, okay? And this is an issue, okay, that can happen. In order to avoid this, we are using here this, where is it? Stratify y, okay? This will do the job and mix it well enough so we won't have this issue. So this is how we split up the data. And now we are using one of the many algorithms of machine learning. And this is sort of the part of the magic or the knowledge or the experience, how to pick which one of the machine learning algorithms to use. So it's not that I have some data, here is a machine, it will give me some results and I can go home, okay? No, you need to select which of these machines you are using to to train. And here I used the logistic regression. There are, I think, hundreds of these different ones. And each one also has parameters. So there's a lot of things that can go wrong, okay? So here we take this logistic regression, which comes from the sklearn library. And we call, forget for the max iter for now, we call the fit method and give it the training data, both the x-axis and the y-axis. So this will run the training part of the machine learning and will return you what they call a model. A model is basically just a function that gets four input data, okay, in this case, okay, because we used this. So in the input, we have 4 input and 1 output, right? So this model will create a function that gets 4 input and gives one output. So this model is basically just a function. Think about it as just a function. Okay? That should be the best to predict from a given 4 values, so from the given measured values, what is the species. Okay, fine. This model actually already have a score, okay, that's called the training accuracy. And this should be, the higher the better. And then you can use the same model and score the test data. So this is the data that the model hasn't seen yet. And we get an accuracy of that. So how accurate the prediction is. The train accuracy, okay, means how well the training worked, how well the model works for the data it was training on. Okay, it won't be 100% most of the cases. Actually, if it's 100%, then it's usually bad because it means it's usually called what they call overfit. So that it fits exactly the training data, but maybe it can't predict the rest of the world. Okay, that can happen because what we really want is that the test accuracy to be high, because that means that on data that it has never seen, how well it can predict the result. And then there is this okay, so that's basically the measurement. And then in the real world, what you would do is take the model, call the predict function on some data sets and get the predictions. Okay, so you would have the measurements, and that's and here we have a report to do that. So I run this, and it's quite fast. It got me the training accuracy. The numbers are between 0 and 1. It's very good training accuracy, very good test accuracy, and so on. It actually told us that it's quite good. Now, one thing I didn't say is the max iteration. Basically, all of these algorithms, the machine learning algorithms, they try to improve themselves and make iterations and iterations and iterations to improve themselves. And the more iteration, usually the better the result is. But of course, it will take more time. So you will have to balance. So it will take more time. And at one point, the improvement in the model is meaningless. Okay. So you say, okay, again, if you have if the precision is too low, then you don't care anymore. So you will have to pick how many iterations you would like it to run. And again, this is something that you will have to experiment with. If we look at the data, this is actually how. Yeah, so these are all the points. If you compare the sepal length with the speckle width, here maybe I should have put this at the beginning. These, we color them, so you can see the different species, each one in different color. Here you can see the series. So how can we predict which one is which? It's probably quite easy because all of them here are one. There's only one outlier, but these are mixed. And maybe we can draw a row here, a line here, and say, well, the best prediction, if it's above here, then these are setosa. Below here, it's either this or that. And if you cut them through here, then you can still separate the green and the orange points here, so the two species. But the logistic function will probably have some better way to predict the data. And I could go on, but we don't have a lot more time. So I will just put the link in there so you can play around further with this example, or you can pick some other example. But this is the basics, right? So have some data, split it up into two parts, one that you're going to use to train the algorithm, and one that you're going to test it, how good it is. So you split it up, you pick some algorithm, okay, some of these algorithms, you run it, get a model, measure how well they are, and then comes the interesting part. How can you improve your data? In many cases, that's the biggest issue, that the data, you don't have enough data, okay, or the data missing some data, incorrect data, outliers, so data that are for some reason are not in the normal thing. Think about all the tomatoes being the same size, and then suddenly you have a huge tomato because I don't know what, and then that's not the normal size, and then it will break the whole thing. So that's it. Any questions? Okay, no questions. 5 minutes left. I'll let you go home soon today. Okay, so that will make you happy. Thank you for being here in the meetings, watching the videos, doing the assignments, taking part in the course. I hope this helps you in some way a little bit, either now, during your studies, or maybe later. Remember, the key is a lot of practice and getting feedback, and it's a long road. I just was in one of the chat rooms, sort of, on I think, whatever someone asked, how long does it take till you get, you feel comfortable writing Python? A few days, I think she asked. I think it's more like a couple of months. And even then, people, even once you feel comfortable, you will find all kind of other things that you don't know yet. And the best is to get feedback from other people. That's it. So thank you very much, and hope to see you in one of those meetings that I'm actually the organizer of most of these meetings I mentioned. So I hope to see you there. Bye-bye. Oh, and don't forget to like the video and subscribe to the channel.